Okay, in this first video problem, what we're going to do is design an LC filter, which in this circuit is simulated as an inductor L, a capacitor C, and a speaker, which is composed of just a resistor R. The input to the system is the voltage VI, which is the music that is being played, and then the output is the voltage V0, which is the voltage across the speaker or the resistor R. The first question would be to find a node that relates V0 and VI, that is output versus input. To do this, we can proceed as we did in class, where we find the currents through the components. So we have IL, IC, and IR. IL is the current at time 0 plus the integral of the voltage across the inductor. IC is C dV0 dt, where V0 is the voltage across the capacitor, and IR is V0 over R. Then a simple Kirchhoff current law says that the current through the inductor is equal to the current through the capacitor plus the current through the resistor. So you see we have an integral, so to get rid of those we can differentiate on both sides. We end up with the expression shown over here. As we've seen in class, it's standard to have the outputs to the left of the equation, the inputs to the right. So here I'm just organizing the equation, and you get this. So you see this is the standard second order form which we've seen in class. So it's V naught double dot plus 2 zeta omega n V naught dot plus omega n square V naught equals f of t. All right. For the second part, what we want to do is find the transfer function. Remember, transfer function is just the relationship output over input in the S domain. So what we do is we take Laplace transforms on both sides, left and right, of the differential equation. There is an assumption that the initial conditions are 0. So by doing this, we end up with this expression, which then we can rearrange algebraically to get the ratio V0 over VI. All right, for the next question, what we want to try to answer is what is V0 in steady state? So what is the output voltage in steady state? What we do is just remember that if you have a linear system where you apply an input sine omega t, the output is going to have a different magnitude and a different phase, where the magnitude is related to the magnitude of the transfer function of the system, where S is equal to j omega. So we need to find h j omega first. We already have h of S, so it's just a matter of replacing S by j omega. All right, and then this is just two complex numbers, so we can compute its magnitude. And that's the answer to the question. Okay, the next part, what we're going to do is just design the filter. So that is, we're going to solve for the inductance and the capacitor that we need, such that our filter performs as follows. We want that frequencies that are larger than 1000 radians per second will be significantly attenuated. This particular frequency of 1000 radians per second is known as the cutoff frequency for our design. We also try to design for a zeta of 0.5, and we will assume that the speaker has a resistance of 1 ohm. The definition of the cutoff frequency says that at that particular frequency, the magnitude of the transfer function will be equal to 0.707. That's just a definition. All right, so let's proceed with this. With the first two equations, 1 and 2, we already had expressions for zeta and omega n. So just rearranging this, we can find that zeta is given by this, which is the same as this expression over here. From here we have first equation, which says that L is RC squared. Now, we already found an expression for the transfer function evaluated at S equal j omega, which can be rewritten as follows, where I'm just replacing omega by 1000. And because I want the cutoff frequency to be 1000, we said that by definition the magnitude of the transfer function will be equal to 0.707. If you solve these two equations together, you find values for L and C. Both end up being the same at 0.00113. If you were to plot the magnitude plot of the body plot for this system, it will look like the following. So you have a cutoff frequency of 1000 radians per second, and you look at the magnitude at this frequency is 0.707. If you set omega equal to 0 or a value smaller than this, you will see from the expression of Hj omega that the magnitude is 1. So you